Good morning, all of you. Today I am going to make an audio recording for visual impaired students of Organic Chemistry book of Dr. G. M. Segal, modern book. Name of the chapter is Alkanes. 4.1 Introduction. The simplest organic compounds are hydrocarbons, the compounds containing only carbon and hydrogen. Depending upon the framework of carbon atoms in their molecules, the hydrocarbons may have either open chain or ring structures. In addition, there may be saturated or unsaturated in character according to the nature of carbon-carbon bonds in them. Due to this variation, hydrocarbons has been divided into different classes. We shall discuss the various classes of hydrocarbons only one by one, starting with alkanes and cycloalkanes. 4.2 Structures of alkanes. Alkanes are open chain saturated hydrocarbons having the general formula CnH2n plus 2, where n is the number of carbon atoms. They contains only single covalent bonds between carbon and hydrogen in their molecules. As such, each carbon atom is bounded to four other atoms, as is clear from the formula of methane, ethane, and propane, the first three members of alkenes. Methane, ethane, propane. The bonds in alkanes are formed by the overlapping of sp3 hybridized orbitals of each carbon atom with similar orbitals of other carbon atom or 1s orbitals of hydrogen atom. As a result, all the four bonds linking the carbon atoms with other atoms are sigma bonds. As these bonds are quite strong and are not easily attacked by other reagents, alkanes do not react with the usual laboratory reagent under ordinary conditions. That is why they are termed as saturated hydrocarbons or paraffins. Latin param little, affin affinity. It may also be noted that due to sp3 hybridization of the carbon atoms of alkanes, the four bonding orbitals of each carbon are directed towards the four corners of a tetragon. For instance, let us consider the case of methane, the simplest alkene. In the formation of its molecule, the four sp3 orbitals of the only carbon atom overlaps the 1s orbitals of the four hydrogen atom, which are situated at the corners of tetrahedron as shown in figure 4.1a. Figure 4.1b represents a molecular model of methane. Figure 4.1c is a simplified three-dimensional representation of the molecule. In this representation, the wedge represents the bond pointing towards the observer out of the plane of the paper. The hatched line represents the bond going away from the observer behind the plane of the paper, and normal lines shows the bond in the plane of the paper. Each carbon hydrogen bond has a length of 110 picometer or 1.10 angstrom, and each HCH angle is 109 degree 28 minute. Figure 4.1d. A overlap of 1s orbitals of 4 hydrogens and sp3 orbitals of carbon. B. Molecular model. C. Simple three-dimensional representation. D. Bond length and bond angles. Figure 4.1 Formation and structure of methane. Similarly, in case of ethane, figure 4.2 and higher alkanes, the relative arrangement of bonds is always tetrahedral, although the different bond angles may be slightly different from the regular tetrahedral value of 109 degree 28 minute. The CH bond length is about 110 picometer 1.10 angstrom, while the CC bond length is 154 picometer 1.54 angstrom or nearly so. Figure 4.2 Molecule of ethane. On account of the tetrahedral arrangement of the four bonds found by each carbon atoms, the molecules of alkanes are three-dimensional in nature. Moreover, in case of alkanes containing more than two carbon atoms, the carbon atoms of the chain do not actually lie along a straight line. This is quite obvious from the model of propane shown in figure 4.3. In fact, for higher alkanes, the carbon-carbon chain can assume a variety of zigzag shapes, but for the sake of convenience, the carbon atoms are written in a straight line so far as possible to have a planar representation as shown below. Molecular model of propane showing that the carbon atoms do not lie along a straight line. Methane, ethane, propane. 4.3 Classification of carbon atoms in alkenes. The carbon atoms present in alkenes can be divided into four categories as given below. First, primary carbon atom 1 degree. It is a carbon atom which is linked directly to either one or nor carbon atom. Second, secondary carbon atom 2 degree. It is a carbon atom which is linked directly to two carbon atoms. Third, tertiary carbon atoms 3 degree. It is a carbon atom which is linked directly to three carbon atoms. Fourth, quaternary carbon atom 4 degree. It is a carbon atom which is linked directly to four carbon atoms. For example, in the formula given below, there are 5 primary, 1 secondary, and 1 tertiary and 1 quaternary carbon atom. CH3, CH2, CH3 on for second position CH3 and fourth position CH3. Hydrogen atoms are also classified as primary 1 degree, secondary 2 degree, and tertiary 3 degree according as they are linked to a primary, secondary, and tertiary carbon atom respectively. Thus, in example given below, there are 15 primary hydrogen, 3 each of on the 5 CH3 groups, 2 secondary hydrogens on CH2 group, and 1 tertiary hydrogen on the CH group. 4.4 Nomenclature of alkenes. The common and IUPAC system of naming the saturated hydrocarbons are discussed below. 4.4.1 The common system. According to this system, the first four members of saturated hydrocarbons have special names, while the higher members are named according to Latin or Greek numeral indicating the number of carbon atoms in the molecules. The names of all the members and in thus formula name CH4 methane, C2H6 ethane, C3H8 propane, C4H10 butane, C5H12 pentane, C6H14 hexane, C7H16 heptane, C8H18 octane, C10H22 decane, C20H42 icosane. In case of isomeric alkanes from C4H10 onwards, the following distinctions are made in naming the various isomers. First, the hydrocarbons having all the carbon atoms in a straight or continuous chain are termed normal or N-hydrocarbons. For example, CH3, CH2 is called N-butane, while CH3 is named as N-pentane. Second, branched chain isomers having tertiary carbon atoms are known as iso, which those containing a quaternary carbon atom are termed neo. For example, CH3CH, CH3CH3 isobutane, CH3CH2CH3 on second position CH3 isopentane, CH3 on second position CH3 and one more CH3 neopentane. 4.4.2 Alkyl group. The removal of one hydrogen atoms from a molecule of an alkane gives a monovalent group called alkyl group. It has the general formula CnH2n plus 2. and is usually represented by the letter R. The names of alkyl group are obtained by replacing the suffix "ane" of the name of corresponding alkene by "yl". It may be possible to get more than one alkyl group from an alkane depending upon the position of the carbon from which hydrogen is removed, as illustrated below. Name and formula of alkene. Formula name and abbreviation of alkyl group. Methane CH4 CH3 methyl amine. Ethane CH3 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 CH2 ethyl eth. Propane CH3 CH2 CH3 1 degree hydrogen, then CH3 CH2 CH2 and propyl and PR. 2 degree hydrogen CH3 CH3 isopropyl PR. And butane CH3 CH2 CH2 CH3 1 degree hydrogen, then CH3 CH2 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 and butyl and Bu. 2 degree hydrogen CH3 CH2 CH3 sec butyl sec Bu. Minus 1 degree hydrogen CH3 CH2 on second position CH3 isobutyl isobu. Isobutane CH3 CH on second then CH3 on second position CH3 3 degree hydrogen CH3C CH3 on second position CH3 tert butyl TBU. 4.4.3 IUPAC system straight chain alkanes. The alkanes in which all the carbon atoms are present in straight chain are named by adding the suffix "ane" to the appropriate word root. For example, CH4 methane, CH3 CH3 ethane, CH3 CH2 CH3 propane, CH3 CH2 CH2 CH3 butane. Branch chain alkenes. In case of branch chain alkenes, the larger possible continuous chain of carbon atom is selected. The corresponding word root followed by the suffix "ane" is written down. The chain is numbered from the end, which gives the lowest number to the carbon carrying the substituent alkyl group. If the number of substituent group is more than 1, numbering is done from the end according to the lowest set of locants from the branching alkyl group. The names of branching alkyl group along with their branchment numbers are there prefixed before the word root in alphabetical order as illustrated below. CH3 CH3 on second position CH3, then 2 methyl propane. CH3 CH2 CH3 on second position CH3, then 2 methyl butane. CH3C CH3 on second position 2 CH3 2 dimethyl propane. CH3C CH2 CH2 CH3 on second position CH3 CH3 on fourth position ethane 4 ethyl 2 dimethylhexane. CH3 CH2 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 CH3 on third position CH3 fourth position CH2 CH3 on sixth position CH3 4 ethyl 3 6 dimethyl octane. Some important points for giving IUPAC names. A few important points to be remembered for IUPAC name of alkanes are given below. First, if two different alkyl groups are equidistant from the two ends of the parent chain, the numbering of the chain is done in such a way that the group which come first in alphabetical order gets the lower number. For example, CH3 CH2 CH2 CH3 CH2 CH2 CH3 on sixth position CH3 and third position CH2 CH3, then 3 ethyl 6 methyl octane. Since ethyl comes ahead of methyl in alphabetical order, the parent chain is numbered from the end, which gives a lower number to ethyl group. Second, if the group attached to the parent chain is also branched, sometimes called complex substituent, is a name or as named as substituted alkyl group by separately numbering the carbon atoms of this group. For this purpose, the carbon atom of this group which is attached to the parent chain is always numbered as 1. The name of such group is always written in brackets. For example, CH3, CH2, CH, CH2, CH, CH2, CH2, CH, CH3. On second position CH3 and fifth position CH2, CH, CH3 and on second position CH3 on seventh position CH2, CH3. 7 ethyl 2 methyl 5 bracket 2 methyl propyl bracket close no name. Third, for deciding their alphabetical order, the complete name of the complex substituent, including the prefixes such as di and tri forming the part of the name, is considered. For example, CH3, CH, CH2, CH2, CH, CH2, CH, CH2, CH2, CH3. On second position CH3, on fifth position CH2, CH, CH, CH3, on second and third position CH3 and seventh position CH2, CH3. 5 bracket 1 2 dimethyl butyl bracket close 7 ethyl 2 methyl decane. The alphabetical order of the name of the complex substituent is decided on the basis of letter D, which is the first letter of the complete name of this group. Fourth, while naming a compound, if two equally long chains are possible but the name of the side chains attached to each possible chain are different, the possible chain having a larger number of side chain is selected as the parent chain. For example, CH3, CH2, CH, CH2, CH2, CH3. On fourth position CH3, on fifth position CH2, CH3, and on third position CH3, and on second position of substituted branch chain, second position CH3. 3,5 dimethyl 2,4 dimethyl octane. Correct parent chain since it has 4 side chains. CH3, CH2, CH, 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 CH2, CH2, CH3. On fourth position CH3, on fifth position CH2, CH3. On third position CH, CH3 and on second position CH3. Incorrect parent chain since it has only 3 side chains. 4.5 Structural isomers in alkanes. Each of the first 3 members of alkanes, methyl, ethane, and propane, methane, ethane, and propane, can have only one structural formula, that is methane, ethane, propane, CH4, CH3, CH3 ethane, CH3, CH2, CH3 propane. However, the higher members from butane onwards can be represented by more than one structural isomers and thus exhibit structural isomerism. The various isomers of the same hydrocarbon differs in the framework of the chain of carbon atoms and therefore isomerism exhibited by alkanes is termed as chain isomerism. For example, butane C4H10 exists in the form of two isomers shown below, CH3, CH2, CH2, CH3 and butane CH3, CH2 on second position CH3 isobutane or 2-methyl propane. Similarly, pentane C5H12 exists in the form of 3 isomers CH3, CH2, 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 CH3 and pentane or pentane CH3, CH2, CH3 on second position CH3 isopentane or 2-methyl butane CH3 on second position 2CH3 neopentane or 2,2-dimethylpropane. C6H14 exists in the form of 5 isomers. C7H16 has 9 isomers and C8H18 has 18 isomers, and so on. Problem 4.1. Draw the structures and write IUPAC names of all possible structural isomers having the molecular formula C6H14, CH3, CH2, 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 CH3 again. CH3, CH2, CH2, CH3 on second position CH3, 2-methylpentane. CH3, CH2, CH2, CH3 on third position CH3, 3-methylpentane. CH3, CH3 on second and third position CH3, then 2,3-dimethylbutane. CH3, CH2, CH3 on second position 2-methyl CH3, 2,2-dimethylbutane. Problem 4.2. Write IUPAC names of the following. First, CH3, CH2, 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 CH3. Second position CH2, CH3. Fifth position CH3. Sixth position CH2, CH3. Second, CH3, CH2, CH3. On third position CH2, CH3. And on fourth position CH2, CH3. Third, CH3, CH2, CH2, CH3. On third position CH3. On fifth position CH2, CH3. On second position CH3. And on second position CH3. Answer. First, 2-ethyl 4,7-dimethylnonane. Second, 4-ethyl 3-methylheptane. Third, 2,8-dimethyl 6(2-methylpropyl (close nonane). 4.6. Natural sources of alkenes. Petroleum, which occurs naturally below the surface of Earth, is a mixture of many hydrocarbons, most of which belongs to alkane series. Natural gas, which issues from a petroleum field, and fuel gases obtained from coal contain lower alkanes. The wax constituents of some plants have also been found to contain alkanes. For example, pine wood and turpentine contains H-heptane, while the leaves of cabbage contains N-non-cosane C29H60. 4.7. General methods of preparation. 4.7.1. The preparation of alkenes by synthetic method is only rarely carried out. The usual practice is to isolate these hydrocarbons, particularly the lower ones, from some suitable natural sources. However, some of the general methods which can be employed for this preparation are discussed below. First, hydrogenation of unsaturated hydrocarbons, Sabatier and Sandrian reaction. Alkenes or alkynes can react with hydrogen in the presence of a catalyst. Finally divided nickel, platinum or platinum to form alkenes. CnH2n alkene plus H2 in presence of nickel, temperature 525 to 575 Kelvin gives CnH2n plus 2. CH2 ethylene plus H2 in presence of nickel gives CH3 CnH2 and minus 2 alkyne plus 2H2 in presence of nickel gives CnH2n plus 2. CH triple bond CH acetylene plus 2H2 in presence of nickel gives ethane CH3CH3. The use of nickel as a catalyst for hydrogenation requires a temperature of about 525 to 575 Kelvin. But if platinum is used as catalyst, the reaction can take place even at room temperature. Methane cannot be prepared by this method, as the starting alkene or alkyl must contains at least 2 carbon atoms. Second, reduction of alkyl halides. Alkyl halides can be reduced directly or through the formation of Grignard reagent to form alkenes. First, direct reduction. The direct reduction of alkyl halides is generally carried out with chemical reducing agents such as zinc and hydroxylic acid, hydrochloric acid, or zinc copper couple and alcohol, or with hydrogen in the presence of platinum catalyst. Rx in presence alkyl halide in presence of Zn or H positive gives RH alkane plus HX. CH3 CH2 CH2 CH2Br N-butyl bromide in presence of zinc plus H positive gives CH3 CH2 CH2 CH3 N-butane plus HBr. CH3 on second position Cl isopropyl chloride plus H2 in presence of platinum gives N-propane CH3 CH2 CH3 plus HCl. The reduction may also be carried out by heating the alkyl halides, particularly with hydrogen iodide in the presence of red phosphorus in a sealed tube. For example, C2H5I ethyl iodide plus HI in presence of red phosphorus gives C2H6 ethane plus I2. Second, reduction through the formation of Grignard reagent. This is an indirect method of reducing alkyl halide. A solution of an alkyl halide in dry ether is treated with magnesium to form an ethereal solution of alkyl magnesium halides, commonly known as Grignard reagent. Rx plus Mg alkyl halide in presence of dry ether gives RMgX alkyl magnesium halides or Grignard reagent. The Grignard reagent are easily decomposed by water producing alkanes. RMgX plus HOH Grignard reagent gives alkane RH plus MgOHX. CH3MgI methyl magnesium iodide plus HOH in presence of CH4 methane plus MgOHX. It may be pointed out that the alkenes and alkyl halide used for the preparation of alkanes by the above mentioned methods are themselves generally obtained from alcohols, but the alcohols cannot be directly converted into alkanes, as the hydroxy group of most alkanes resist reduction to corresponding alkenes. Third, Wood's reaction. This reaction brings about the union of two alkyl radicals by the action of metallic sodium upon alkyl halides and dry ether. The resultant products are alkanes with a carbon skeleton having a higher number of carbon atoms than the reacting alkyl halides. Rx alkyl halide plus 2Na plus X R dry ether gives RR alkanes plus 2NaI. CH3I methyl iodide plus 2Na plus ICH3 in presence of dry ether gives CH3CH3 ethane plus 2NaI. CH3CH2Br ethyl bromide plus 2Na plus Br CH2CH3 dry ether gives CH3, CH2, CH2, CH3 and butane plus 2 NaBr. It may be noted that when the reaction involves two molecules of the same alkyl halides, asymmetric alkenes, that is RR, having an even number of carbon atoms is formed. For preparing an unsymmetric alkanes containing 3 or more than 3 carbon atoms, for example propane, a mixture of different alkyl halides has been used. CH3Br methyl bromide plus 2Na plus BrCH2 CH3 ethyl bromide in presence of dry ether gives CH3 CH2 CH3 propane plus 2NaBr. But the product obtained by using different alkyl halides consists of mixture of alkanes which cannot be easily separated. This is because the two alkyl halides also react separately with sodium to form two more hydrocarbons as a product of the side reaction. Thus, in case of above reaction, ethane from CH3Br and Na and butane from C2H5Br and Na are also obtained. The main feature of Wood's reaction is that it leads to the formation of carbon-carbon bond. As such, the reaction can be employed for preparing compounds containing higher number of carbon atoms from those containing lesser number of carbon atoms. For example, ethane may be obtained from methane as follows: CH3 plus Cl2 gives CH3Cl plus HCl. CH3Cl plus 2Na plus Cl CH3 gives CH3CH3 plus 2NaCl. The order of reactivity of different alkyl halides in the reaction: idos, then bromodes, then chlorides. Limitation of Wood's reaction. First, it is suitable only for the preparation of symmetrical alkanes RR. Second, it cannot be used for the preparation of methane. Third, tert alkyl halides cannot be used in the reaction. Mechanism. Two mechanisms has been suggested for this reaction. These are: first, intermediates formation of free radicals. According to this mechanism, it is believed that the alkyl halides first forms alkyl radicals which combine with one another to furnish in the hydrocarbons. Thus, Rx plus Na gives R free radical plus NaX. R free radical plus R free radicals gives RR hydrocarbon. This mechanisms operate when the reaction is carried out in vapor phase. Second, intermediate formation of an organometallic compound. Here, the reaction is believed to take place through the formation of organometallic compound as intermediate. For example, Rx plus 2Na gives Rna plus NaX, and Rna plus Xr gives Rr plus NaX. This mechanism operates when the reaction is carried out in solution. For Corey house synthesis, this method was developed around 1970 and is a much better method than Wood's reaction for preparing alkanes containing higher number of carbon atoms than the reactants taken. It consists of a reaction between an alkyl halides and a lithium dialkyl copper. R-X alkyl halide plus R2Cu Li lithium dialkyl copper. R and R may be same or different. R alkane plus RCu plus LiX. For example, CH3, CH2, CH2, CH2Br and butyl bromide plus CH3 to Cu Li lithium dimethyl copper, CH3, CH2, 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 CH3 and pentane plus CH3Cu methyl copper plus Lib. Lithium dialkyl copper required in the reaction is itself prepared from alkyl halides as illustrated below. Rx plus 2 Li ether RLi plus LiX. 2 RLi plus CuX gives to R2 CuLi plus LiX. To obtain a good yield of alkenes, alkyl halides used in generally primary alkyl halides, which the alkyl groups in lithium dialkyl copper may be primary, secondary, or tertiary. An important feature of this reaction is that it can be used for preparing all types of alkanes, whether symmetrical or unsymmetrical, whether straight chain or branch chain. Mechanism. In the beginning, the alkyl group of alkyl lithium displays halogen from copper halide to form alkyl copper. CuX plus RLi gives RCu plus LiX, alkyl copper. Alkyl copper reacts further with alkyl lithium to form lithium dialkyl cuprate. LiR plus Cur gives R2Cu negative plus Li positive. Alkyl halides then undergoes nucleophilic attack by dialkyl cuprate anion to generate an unstable intermediate which decomposes to gives the final product. R2Cu negative plus R dash X gives R2Cu R double dash X bracket minus gives R dash plus RCu plus X negative. 5. Kolbe electrolytic reaction. In this reaction, concentrated aqueous solution of sodium or potassium salts of monocarboxylic acid is subjected to electrolysis to get alkanes. 2RCOONA plus 2H2O electrolysis RR alkane plus 2NaOH H2. The reactions take place as follows. 2RCOONA sodium salt of the acid ionization 2RCOO negative plus 2Na plus 2RCOO negative minus 2 electrons gives 2RCOO gives RR plus 2CO2 alkane at the cathode. 2H2O ionization gives 2H positive plus 2OH negative. 2H positive 2H positive plus 2 electrons gives H2 at the cathode. The discharge potential of H positive ions is lower than that of Na positive ions. Therefore, H positive ions are discharged at the cathode, liberating H2, while Na positive ions remains in solution. For example, 2CH3COO gives CH3COO negative plus 2Na positive. Sodium acetate or sodium ethanoate 2CH3COO negative minus 2 electrons gives 2CH3COO gives CH3CH3 plus 2 COO2 at the anode. 2H positive plus 2 electron gives H2 at the cathode. This is a good method for preparing ethane and higher alkanes having even number of carbon atoms. Methane cannot be prepared by this method. 6. Decarboxylation of monocarboxylic acid. When heated with soda lime NaOH plus CaO, sodium salt of monocarboxylic or fatty acid undergoes decarboxylation to form alkanes. The reaction involves the elimination of carbon dioxide from carboxylic group. Active components of sodium lime in this reaction is NaOH, but it is now employed as such because It melts on heating and is deliquescent as well as RCOO, sodium salt of fatty acid, plus NaOH gives CaO, RH alkanes plus Na2CO3. CH3COO, Na plus NaOH, sodium acetate gives methane, CH4 plus Na2CO3. Oakwood and co-workers 1950 has shown that the reaction proceeds according to the above equation only in case of sodium acetate. In case of higher members, various side products are also obtained. Thus, in case of sodium propanoate, the reaction gives methane, hydrogen, and certain unsaturated hydrocarbons also in addition to ethane. It may be pointed out that alkanes are also formed during some other chemical reactions, but these reactions are not employed for the actual preparations of alkanes either because of the poor yield of the desired products or some other drawbacks. 4.7.2 Preparation of methane. Beside method number 2, 4, and 6 described above, methane can be prepared conventionally by dropping water over aluminium carbide as Al4C3 aluminium carbide plus 12H2O gives 4AlOH thrice plus 3CH for methane. The gas obtained by this method is generally contaminated with hydrogen and acetylene. 4.7.3 Preparation of ethane. Although ethane can be prepared by any of the general methods of preparation, it is generally prepared in the laboratory by the reduction of ethyl iodide or ethyl bromide with the nascent hydrogen produced by the action of zinc copper couple on ethyl alcohol. 2C2H5OH ethyl alcohol plus Zn gives Cu C2H5O twice Zn zinc ethoxide plus 2H. Then CH3CH2I ethyl iodide plus 2H gives CH3CH3 plus Hi. 4.8 Physical properties of alkanes. 4.8.1 Physical state. The lower members of alkanes containing up to 4 carbon atoms are colorless gases. The higher normal alkanes having 5 or 7th carbon atoms are colorless liquids, and beyond that they are colorless solids at room temperature. 4.8.2 Boiling points. The boiling points of an alkanes increases regularly with the increasing number of carbon atoms. There is an increase of about 2 to 30 degrees for each carbon atoms added to the chain, except in the first few cases where the increase in much more. This can be explained in terms of intermolecular forces of attraction. Alkenes are non-polar compounds having weak van der Waals forces of attraction between their molecules. These forces act along the surface of molecules and their magnitude increase with the increase in surface area. As the molecular size of alkenes increase, the surface area and strength of van der Waals forces also increases. As a result, the boiling point also increase. Amongst the isomeric alkanes, there are small differences in the boiling points of various isomers. The branched chain isomers have invariable lesser boiling points than the normal compounds, and the greater the branching, the lower is the boiling point of branched isomers. For instance, the boiling points of N-pentane, isopentane, and neopentane are 309, 301, and 282.5 Kelvin respectively. This is due to the fact that branched isomers are more compact, that is, they have lesser surface area than their normal counterparts due to lesser surface area of such molecules. The van der Waals force of attraction operating between them are comparatively weaker. As such, lesser energy is needed to overcome these forces from the boiling to take place, and therefore their boiling point are lower. 4.8.2 Melting points. The melting points of alkenes do not show a very smooth graduation with the increase in molar size. For instance, let us consider the melting point of N-propane to N-octane. Hydrocarbon normal isomers C3H8 melting point 85.9, C4H10 138, C5H12 143.3, C6H14 179, C7H16 182.5, C8H18 216.2. It may be seen that increase in melting point is much more in moving from an alkane having odd number of carbon atoms to the higher alkane, that is than in moving from an alkane having even number of carbon atoms to the higher alkane. This is essentially because the intermolecular forces in a crystal depends upon only upon the size of the molecule but also upon how well the molecules fit into the crystal lattice. It has been already made clear that the carbon in alkanes form a zigzag type of chain rather than straight chains. Now, in N-alkanes containing an even number of carbon atoms, the terminal methyl group lies on the opposite side of the zigzag chain. On the other hand, in case of N-alkanes having odd number of carbon atoms, the terminal methyl group lies on the same side of the chain as shown below. CH3, CH2, 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 CH3, N-hexane even number. CH3, CH2, 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 CH3, and heptane odd number. It appears that the alkenes having an odd number of carbon atoms do not fit in so closely together in the crystal structure as the alkenes having an even number of carbon atoms. As a result, the energy required to break the crystal structure and thus melt the alkenes is lesser in case of alkenes having odd number of carbon atoms. That is why they have a lesser than accepted melting point, as shown by only a slight increase in a melting point in moving from an even number alkenes to the higher odd number alkenes. 4.8.4 Specific gravity. The specific gravities of alkenes also increase with increasing molecular weight but becomes constant at about 0.8. This implies that all alkenes are lighter than water. 4.8.5 Solubility. Due to nearly same electronegativities of carbon and hydrogen atoms present in them and the symmetrical shapes of their molecules, alkanes are non-polar in character. As such, they are insoluble in polar solvents such as water but dissolve freely in non-polar solvents such as ether. The solubility decreases with increase in the molecular weight. 4.9 Chemical properties. The molecular structure of alkenes involves only carbon-carbon and carbon-hydrogen single bond. As all these bonds are sigma bond and are practically non-polar in nature, alkanes constitute a rather unreactive class of compounds. These are quite inert towards the common reagents such as acids, alkalis, and oxidizing or reducing agent under ordinary condition. However, under strong conditions, alkanes do undergo a few reactions, mostly involving substitutions. The reaction generally take place by free radical chain mechanism. The important reactions of alkane are described ahead, not included in the syllabus. First, halogens. This reaction involves the replacement of one or more hydrogen atoms of an alkane by a corresponding number of halogen atoms. Chlorination and bromination are carried out by treating the alkane with chlorine or bromine in the presence of light, sunlight, or ultraviolet light, or at a high temperature 525-673 Kelvin. For example, when chlorine reacts with methane under these conditions, all the four hydrogen atoms of methane can be successfully replaced by chlorine atom as shown below. CH4 methane plus Cl2 gives CH3Cl methyl chloride chloromethane plus HCl. CH3Cl plus Cl2 gives CH2Cl2 methylene chloride dichloromethane plus HCl. CH3Cl plus Cl2 gives CHCl3 chloroform dichloromethyl plus HCl. CHCl3 plus Cl2 gives CCl4 carbon tetrachloride tetrachloromethane plus HCl. Bromination, though similar to chlorination, take place less readily. Iodination of alkanes is extremely slow and reversible. CH4 plus I2 gives CH3I plus HI methyl iodide. Therefore, direct iodination of alkanes cannot be brought about. However, the reaction may be carried out in the presence of an oxidizing agent such as iodic acid, nitric acid, etc., which converts the hydrochloric acid produced in iodine. 5HI plus HiO3 gives 3I2 plus 3H2O. Fluorination. Fluorination of alkenes is not generally carried out because it takes place with explosive violence. Moreover, fluorination often involves extensive rupture of carbon-carbon as well as carbon-hydrogen bonds. The reaction can be made less vigorous by diluting fluorine with an inert gas such as nitrogen or argon. It is obvious, therefore, that the order of reactivity of halogens towards alkanes is fluorine, chlorine, bromine, iodine. Halogens of higher alkanes. The formation of isomeric halogen derivatives. The halogen of higher alkanes yield a mixture of all possible isomeric halogen derivatives. For example, chlorination of propane gives a mixture of 1-chloropropane and 2-chloropropane. CH3 CH2 CH3 propane plus Cl2 minus HCl gives 1-chloropropane CH3 CH2 CH2Cl 2-chloropropane CH3 CHCl CH3. Further chlorinations gives a mixture of 4 disubstitution products which are shown below. CH3 CH2 CHCl2 1 dichloropropane CH3 CHCl CH2Cl 1 dichloropropane CH2Cl CH2CH2Cl 1 dichloropropane CH3 CCl2 CH3 2 dichloropropane. The mechanism of halogens is discussed a little later. Note, it may be seen that halogens of alkanes is an oxidative process because it involves a replacement of electropositive hydrogen atoms by electronegative halogen atoms and is accompanied by an increase in the oxidizing state of carbon. Second, nitration. This reaction involves the substitution of an hydrogen atoms of an alkane by a nitro N double bond O and single bond O group. It is carried out by heating the hydrocarbon in the vapor state with nitric acid at about 700 Kelvin. RH alkane plus HNO3 in presence of in temperature of 700 Kelvin gives RNO2 nitroalkane plus water H2O. During nitration, rupture of carbon-carbon bonds in some of the molecules also takes place. As a result, the reaction furnishes a mixture of different products. For example, the nitration of propane results in the formation of a mixture of 4 nitro compounds as shown below. CH3, CH2, CH3, HNO3 in gives temperature 673 Kelvin. CH3, CH2, CH2, NO2, 1 nitropropane plus CH3, CHNO2, CH3, 2 nitropropane, 2 nitropropane plus CH3, CH2, NO2, nitroethane plus CH3, NO2, nitromethane. Third, sulfonation. It is a reaction involving the replacement of an hydrogen atoms of an alkane by a sulfonic acid SO3H group. Only higher alkanes undergo sulfonation by reacting with the fuming sulfuric acid. For example, C6H14 hexane plus H2SO4 in presence of SO3 gives C6H13SO3H hexane sulfonic acid plus H2O. Nitration and sulfonation are believed to take place by free radical mechanism. Fourth, oxidation. First, combustion. When burst in excess of air or oxygen, alkanes undergoes complete oxidation to produce carbon dioxide, water, and large quantities of heat. CnH2n plus 2 plus O2 excess gives N CO2 plus N plus 1 H2O plus heat. For example, CH4 plus 2O2 gives CO2 plus 2H2O. Delta H is equal to minus 890 kilojoule. And 2C2H6 plus 7O2 gives 4CO2 plus 6H2O. Delta H is equal to minus 3110 kilojoule. In spite of being highly exothermic reaction, combustion requires a high temperature, that of a flame, to start it. This is due to the energy of activation required to initiate the reaction. Due to the large quantities of heat produced during combustion of alkanes, this reaction has tremendous practical importance. Vast quantities of hydrocarbons obtained from petroleum are used as fuels from the production of heat and power by combustion. The cooking gas, commonly known as LPG, that is liquefied petroleum gas, is a mixture of propane and butane compressed as liquids. Incomplete combustion of alkanes due to insufficient supply of air or oxygen results in the formation of soot or carbon black. This is used in the manufacture of Indian ink, printer ink, black varnish, and as a filler for rubbers. Second, catalytic oxidation. When heated in a regulated supply of air or oxygen at high pressure in the presence of a suitable metallic catalyst, lower alkanes are oxidized to alcohol and aldehydes, which higher homologous yield long chain fatty acids. For example, when a mixture of methane and oxygen in suitable proportion is compressed to 100 atmospheres and passed through copper tubes at 475 Kelvin. Methane is oxidized to methanol 2CH4 plus O2 in presence of 475 and 100 atmosphere. Cu tube gives 2CH3OH. When a mixture of methane and oxygen is passed through heated molybdenum oxide, methane is oxidized to formaldehyde. CH4 plus O2 in presence of MO2O3 gives HCHO plus H2O. Third, normally alkanes resist the action of oxidizing agents such as potassium permanganate, but alkanes containing tertiary hydrogen atoms can be oxidized by such reagents to corresponding alcohols. For example, CH3 and on second position CH3 isobutane plus O in presence of alkyl KMNO4 gives CH3COH CH3 and second position CH3. Third butyl alcohol. 5. Thermal decomposition or pyrolysis. This process involves the decomposition of bigger molecules into a number of simple molecules by the action of heat. When heated to about 775 to 1075 Kelvin, higher alkanes undergo pyrolysis to yield smaller molecules. For example, propane decomposes as follows at about 735 Kelvin. CH3, CH2, CH3 propane temperatures 3 7 735 Kelvin gives ethylene plus methane CH2 double bond CH2 plus CH4 55%. CH3 CH double bond CH2 propylene plus H2 45%. It is apparent that pyrolysis involves the decomposition of carbon-carbon as well as carbon-hydrogen bonds. The composition of products depends upon the nature of starting compounds and condition employed. The pyrolysis or thermal decomposition of alkanes obtained from the petroleum is commonly referred to as cracking or fragmentation. So, cracking is a very important process from a commercial point of view, as is discussed in detail under petroleum. 6. Catalytic reforming or aromatization. This process concerns the conversion of aliphatic hydrocarbons into aromatic hydrocarbons in the presence of suitable catalyst. The reaction involves dehydrogenation, cyclonation, and even isomerization in some cases. It is generally carried out at high temperature of about 720 to 820 Kelvin, high pressure 10 to 20 atmospheres, and in the presence of a catalyst which generally consists of a chromic oxide supported on aluminium oxide. Thus, an hexane changes into benzene and an heptane changes into toluene. CH3, CH2, 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 CH3 and hexane in presence of 770 Kelvin, 1020 atmosphere. Cr2O3 Al2O3 gives benzene plus 4H2O. CH3, CH2, 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 CH3 and heptane in presence of 770 Kelvin, 10 to 20 atmosphere. Cr2O3 Al2O3 gives toluene plus 4H2O. These days, the reaction is generally carried out at 670 Kelvin in the presence of platinum as a catalyst. Therefore, the reaction is sometimes termed as platforming. 7th, isomerization. It is a process of converting one isomers into another. It is found that when N alkanes are heated in the presence of aluminum chloride and hydrogen chloride, they are converted into branch chain isomers. For example, CH3 CH2 bracket 4 and CH3 and hexane in presence in temperature 375 Kelvin. AlCl3 and HCl gives 2-methyl pentane. CH3 CH CH2 CH2 CH3 second position methyl CH3 CH3 CH2 CH CH2 CH3 on third position methyl CH3 3-methyl pentane. 4.10 Mechanism of halogenation of alkanes. Mechanism of halogenation. The halogenation of alkanes is known to be a free radical chain reaction. This is because it proceeds through a series of steps involving free radicals, each step generating a free radicals that brings about the next step till the chain of these steps is finally broken. There are three fundamental stages of the chain reaction, namely A. Chain initiation step, B. Chain propagation step, C. Chain terminating step. Let us discuss the mechanism of hallucination by considering the chlorination of methane. A. Chain initiating step. The reaction is initiated by the homolytic cleavage of a chlorine molecules into two chlorine molecules or free radicals, each carrying an odd or unpaired electrons. The energy required for this is supplied by heat or light. First, Cl heat 523 to 673 Kelvin or light gives 2Cl dot chain initiating step. B. Chain propagating step. Once the chlorine atoms or free radicals are formed, each of them reacts with the methane molecules, forming hydrochloric acid and generating a methyl free radical as shown in step 2. Each of the methyl radicals in turn reacts with another chlorine molecules to form methyl chloride and at the same time generates another chlorine atoms or free radicals as shown in step 3. These newly formed chlorine atoms can react with another molecules of methane as shown in step 2 to produce another molecules of hydrochloric acid and another methyl free radical. The methyl free radical can again repeat the step 3 and so on. Thus, step 2 and 3 are repeated several times and the chain gets propagated till it's ultimately terminated. Second, CH3 uh, H plus Cl radical gives HCl plus CH3 radical. Third, CH3 radical plus Cl gives CH3Cl plus Cl radical. Chain propagating step which are repeated several times. The chlorine atoms formed in step 3 can also react with the methyl chloride formed to yield hydrochloric acid and a new substituted methyl radical as shown in step 4. The substituted methyl radical would react with another molecules of chlorine to form dihalogenate methane as indicated in step 5. Theoretically, this process may extend further till all the replaceable hydrogen atoms in the methane molecules has been substituted by chlorine. Fourth, Cl free radical plus CH3Cl from step 3 gives HCl plus CH2 radical Cl. Fifth, Cl plus CH2Cl radical gives CH2Cl2 plus Cl radical. Sixth, Cl radical plus HCHCl2 gives HCl plus CHCl2 radical. Seventh, Cl plus CHCl2 radical gives CHCl2 Cl3 plus Cl radical. 8th, Cl radical plus HCl3 gives HCl plus CCl radical. 9. Cl plus CCl3 radical gives CCl4 plus Cl radical. Further chain propagating step in case of formation of di and polyhalogenated alkanes. 6. Chain terminating step. The chain of reaction initiated and propagated as outlined above may be terminated if the free radicals combine amongst themselves without giving rise to any new radicals as shown below. Cl radical plus Cl radicals give Cl2. CH3 radical plus Cl radical gives CH3Cl. CH3 radical plus CH3 radicals give CH3CH3. Possible chain terminating step. The chance of free radicals combining amongst themselves are very low. Indeed, because of the very small relative concentrations of free radicals in the reaction mixture. Still, such a combination cannot be completely ruled out. As this happens, the chain of a step initiated by the cleavage of a particular chlorine molecules comes to an end, but other similar chains initiated by other chlorine molecules continue to operate, and therefore the overall reactions keep on progressing. Evidence in support of the above mechanism. The free radical mechanism of hallucination is supported by the following facts. First, the reaction does not take place in the dark at ordinary temperature but requires energy in the form of heat 525 to 675 Kelvin or light to initiate the process. This is because the reaction initiating step involves the uh, dissociation of halogen molecules into free radicals, which requires the supply of energy. Second, high quantum yield. For each photon of energy absorbed, many thousand molecules alkyl halides are formed. This is evidently due to the repeating chain propagating step. Third, it has been observed that addition of substances that are sources of free radicals can initiate the reaction in the dark at temperature below 525 Kelvin. For example, in the presence of 0.02% of tetraethyl lead 6-H5 4 Pb, chlorination of methane proceed in the dark at 415 Kelvin. CH4 plus Cl2 in presence of 415 Kelvin 0.02% C2H5 4 Pb gives CH3Cl plus HCl. It is also known that at 415 Kelvin tetraethyl decomposes to give metallic lead and ethyl free radical. C2H5 4 Pb in presence of 415 Kelvin gives Pb plus 4 C2H5 radical. It appears quite reasonable that the ethyl radicals formed in the manner attack chlorine molecules to produce chlorine atoms or free radicals. C2H5 radical plus ClCl gives C2H5Cl plus Cl radical. The chlorine atoms thus generated then start the chain propagating step and the reaction progresses. Similarly, the reaction proceeds at lower temperature in the presence of benzoic peroxide because it generates free radicals at lower temperature. Fourth, role of inhibitors. An inhibitors is a substance that can slow down or although stop a reaction even when present in small quantity. It has been observed that oxygen acts as an inhibitor in the hallucination of alkenes. This is believed to be due to the fact that an oxygen molecules combine rapidly with an alkyl radical to form the comparatively much lesser reactive peroxyl alkyl radical R radical plus OO double bond between them gives ROO radical. As the new radical cannot continue the chain gets terminated. Thus, each oxygen molecule breaks a chain by combining with an alkyl radical and thus stop the formation of thousands of molecules of alkyl halides. This naturally slows down the rate of the reaction. Of course, when all the oxygen molecules have been used up, the reaction proceeds normally. 4.11 Some important aspects of hydrogenation of alkenes. We now discuss some important and interesting aspects of halogenations of alkenes. 4.11.1 Relative reactivities of halogens in a halogenation of alkenes. The order of reactivity of halogens in the various halogenation reactions of alkanes has been found to be F2, then Cl2, then Br2, then I2. In fact, in case of iodine, the reaction does not seem to take place at all. We would try to account for this observed order of reactivity by considering the energy changes during the chain initiating or propagating a step in the reaction of a particular alkane, say methane, with different halogens. Since energy of E activation has not been measured for the various steps of all the reactions, the value of delta H for different steps derived from the bond dissociation energy would be of a lot of help to us. The values of delta H for each of the three most important steps during halogenation of methane with various different halogens are as follows. Various step X is equal to FClBrI. First x2 gives 2x radicals. Delta H is equal to plus 159 plus 242.5 plus 192.4 plus 151 in kilojoule. Second, x dot plus ch4 gives hx plus ch3 dot delta H is equal to minus 133 plus 4 plus 637 plus 138. Third, ch3 dot plus x2 gives ch3x plus x dot gives minus 292 minus 108 minus 100 minus 84. The first step merely involves the dissociation of halogen molecules, and therefore delta H can be taken to be equal to E act. Thus, iodine having the least E act should dissociate, most probably followed by fluorine, bromine and chlorine in this order. But this order of dissociation goes against the observed order of reactivity of halogens. This means that the first step cannot be responsible for the observed order of reactivity. The third step involves the reaction of a methyl radical with halogens is found to be exothermic in all the four cases, and the value of delta H is nearly the same for chlorine, bromine and iodine for all these reactions. E act is accepted to be quite small, and the actual value is possible not more than fraction of a kilojoule in any case. Thus, this step also cannot explain the observed reactivities, as it appears to take place with equal ease in all the cases. Coming to the second step, which involves the extractions of hydrogens of methane by halogen atoms, we observed a wide variation of in the value of delta H. This value of E act for this step are found to be 17 kJ and 75 kJ respectively. For reactions involving chlorine and bromine atoms, in case of highly exothermic reactions with fluorine atom, the E act is accepted to be a very low, about 1 to 2 kJ, while for the highly endothermic reactions with iodine at atom, E act must naturally be at least 138 kJ. This implies that a fraction of effective collision in the step should be in order of fluorine, then chlorine, then bromine, then iodine. It is these fractions of effective collisions which controls the overall reactions. For instance, the actual fraction of effective collisions between chlorine atoms and methane is found to be 1 in 40 and 548 Kelvin, while it is 1 in 10 million in case of bromine atoms and methane at the same temperature. Due to the very small fraction of its effective collisions with methane, it is quite likely that a bromine atom may happen to collide against another bromine atom or an methyl radical during its searches for a reaction involves a particular bromine atoms may get terminated before long. It is found in actual practice that average chain length involves bromine is less than 100, while in case of chlorine it runs into several thousands. It is therefore evident that the rate of chlorination of methane and other alkanes should be much faster than bromination, in spite of the fact that chlorine molecules dissociate into atoms. Step 1. More closely than bromine molecules. In case of fluorination, fluorine atoms are not only formed faster than chlorine or bromine atoms due to lower reactive of step 1, but also the length of reaction chain are much longer due to reactive of step 2 being only about 1 to 2 kilojoule. At the same time, the overall fluorination reaction is highly exothermic, delta H being minus 427 minus 104.5 and minus 34.5 kilojoule respectively in case of overall processes of fluorination, chlorination and bromination. All these factors takes together ample justifies the explosive nature of fluorination of alkenes. For ionization to be carried out, act for a second step must be at least 138 kilojoule. Even with this value, the fraction of effective collision between methane and iodine atoms works out to be 1 in 10 power 12 at 548 Kelvin. Evidently, this is too low a fraction to allow any reaction propagating chain to function. This is why iodination takes place only at a negligible rate, even though iodine atoms are formed from their molecules at a comparatively fast rate due to low react of step 1. It may be noted that the most vital steps in halogenation, that is step 2, involves the formation of halogen acids. Now, the bond dissociation energy of HF, HCl, HBr, HI are 569, 430, 368, 297 kilojoule molecule, kilojoule per mole. The order of hydrogen halogen bond strength, it may be seen if the same as the order of reactivity of halogens in halogenation of alkenes. This indicates that the reaction of halogens towards alkenes is linked with the strength of hydrogen halogen bonds. The more the strength of hydrogen halogen bonds, the more the reactivity of halogens in the halogenation of alkenes. Further, the strength of hydrogen halogen bond determines the stability of halogen acids. Therefore, it may be also be stated that more the stability of halogen acids formed during halogenation, more is the reactivity of halogen. To conclude this decision, it may be emphasized that the most important and rate determining step is the halogenation of alkenes, is the chain propagating step 2. It is also be noted that overall halogenation of alkenes, except iodination, proceeds at quite a fast rate, even though the EACT for the chain initiating step is quite high. This is because the decomposition of even one molecule of halogens leads to the formation of many molecules of alkyl halides due to the repetition of step 2 and step 3 time and again. Thus, the overall reaction works out to be quite fast in spite of initial slow dissociation of halogens. 4.11.2 Transition state for halogens. It has been already stated that the vital step in the halogenation of alkenes is RH plus X radical gives R radical plus HX. The energy of activation for this step, which controls the whole process, is obvious, equal to the difference in energy between the reactants and the transition state. Let us have a close look at this transition state, the formation of which is so important for the progress of halogenation. In this transition state, the carbon-hydrogen bonds of the alkenes is somewhat stretched but not completely broken, while a new hydrogen halogen bond has been partially formed. At the same time, the odd electron, which is on halogen in case of reactants, on alkyl group in case of product, is divided between the two in the transition state. For dispatching such a state, dotted lines may be used for indicating partially broken and partially formed bonds, while the symbol del may be employed for representing each atom shared of the odd electrons as shown below. RH plus X radical gives RH X transition state, R radical plus HX product. The transition state leading to the formation of a particular free radical has some of the properties of the free radicals. Thus, the free radicals and the corresponding transition states have the same order of stability and ease of formation. 4.11.3 reactivities of alkanes in halogens and relative reactivities of different classes of hydrogen atoms. If a mixture of equimolar amounts of two or more alkanes is allowed to react with a limited quantity of chlorine or bromine, the product obtained consists of a mixture of different alkyl halides corresponding to the alkane taken, but the reactive quantities of alkyl halides in the mixture are not the same. This means that different alkanes exhibit different degrees of reactivity while reacting with a particular halogens. These relative reactivities of alkanes can be attributed to the reactivities of the different classes of hydrogen atoms present in them. It has been found that irrespective of the alkanes in which they are present, the relative reactivity of different hydrogen atoms follows the order tertiary, then secondary, then primary. The hydrogens of methane being lesser reactive than even primary hydrogens. To have an idea of the magnitude of difference in the reactivities of different hydrogen atoms, let us consider the reaction between a mixture of equimolar amount of ethane and methane and a small quantity of chlorine at 298 Kelvin in the presence of light. It is found that the amount of ethyl chloride formed is about 400 times as much as that of methyl chloride. CH4 plus CH3 gives Cl2. 298 Kelvin light CH3CH2Cl 400 parts plus CH3Cl 1 part. This means that ethane is 400 times as reactive as methane, allowing for that fact that ethane contains 6 hydrogen atoms while methane has only 4. Each primary hydrogens of ethane is still about 267 times, that is 400 into 4 by 6, as reactive as each hydrogen of methane. The relative reactivities of different classes of hydrogen atoms may be explained by considering the relative stabilities of alkyl radicals formed in the step which controls the overall process of halogenation. For instance, in case of chlorination of methane and ethane, the respective rate controlling step may be written as CH4 plus Cl radical gives CH3 radical plus HCl. CH3 plus Cl radical gives CH3 CH2 radical plus HCl. Relative to the respective parent alkanes, ethyl radical, a primary radical, is more stable than methyl radical. As such, the transition state leading to the formation of this radical must be more stable than the transition state generating methyl radical. Consequently, the transition state of ethyl radical must have lesser act than the transition state of methyl radical. Therefore, the transition state in the former case must be formed more radically than the latter. In other words, the carbon-hydrogen bonds in ethane gets stretched and ultimately breaks more readily than the carbon-hydrogen bond in methane. That is why primary hydrogen atoms in ethane are said to be more reactive than the hydrogen atoms in methane. Similarly, the still greater reactivities of secondary and tertiary hydrogen atoms can be explained in terms of greater stabilities of secondary and tertiary alkyl radicals. Thus, it may be concluded that the activities of different classes of hydrogen atoms which determine the relative rates of halogenation of different alkenes follows the same order as that of relative stabilities of corresponding alkyl radicals, that is tertiary, then secondary, then primary, then methane. 4.11.4 Orientation of halogenation. It has been observed that sometimes a compound can form different products on a reaction with the same reagent. This means that the compound has more than one reactive sites, whereas the attacks by the given reagent can take place. The process of determining the particular sites or sites in a molecules where the reaction is most likely to occur is known as orientation. It involves the examination of factors which can influence the relative rates of compacting reactions. For the present, let us consider the orientation of halogenation of alkenes. It has been pointed out earlier that the halogenation of higher alkenes can lead to the formation of two or more isomeric products. For instance, the chlorination of propane at room temperature produce a mixture of N-propyl chloride CH3CH2CH2Cl and isopropyl chloride CH3CHCl in the ratio 45:55. The rate controlling step for the two competing reactions involves the formation of N-propyl and isopropyl radicals by the abstraction of a primary or a secondary hydrogen of propane as shown below. CH3CH2CH3 plus Cl radical gives CH3CH2CH2 radical plus HCl. Another CH3CH radical CH3 plus HCl. Naturally, the relative quantities of the two halides produced would depend upon the relative rates at which N-propyl and isopropyl radicals are formed. Let us examine the various factors, that is collision frequency, probability factor, and energy factor, which can influence the rate of formation of these radicals. First, collision frequency. As far as the collision frequency is concerned, it must be same for the two reactions since the same particles, that is propane molecules and chlorine atoms, are involved in each case. Second, probability factor. The probability factor concerns the orientation of propane molecules at the time of attacking by chlorine atoms. For the formation of N-propyl radicals, the propane molecules must be so orientated at the time of collisions that the chlorine atom strikes against the primary hydrogens which get abstracted. Similarly, the formation of isopropyl radicals would require the propane molecules to be there are 6 primary and 2 secondary hydrogens in each molecules of propane. Therefore, the probability factor should favor the formation of N-propyl radical by the abstraction of hydrogen in the ratio 6:2 or 3:1. Third, energy factor. It is evident that the combined effect of collision frequency and probability factor would require the formation of N-propyl chloride and isopropyl chloride in the ratio 3:1. However, the actual ratio of products formed is 45:55 or roughly 1:1. The proportion of isopropyl chloride is thus about 3 times than accepted value. This means that about 3 times as many collisions with secondary hydrogens are reactive as compared to the collision with primary hydrogen. This is quite in keep with the influence of energy factor. Since isopropyl radical, a secondary radical, is more stable than n-propyl radical, a primary radical, the transition state leading to the formation of former radicals must also be more stable and therefore has lesser energy of activation. In other words, E actor for the abstract of secondary hydrogens and consequent formation of isopropyl radical is lesser than that of abstractions of primary hydrogens and formation of n-propyl radical. That is why the formation of isopropyl chloride take place preferentially. Similarly, investigations involves chlorination of other alkenes indicate that the reactive proportion of various isomeric chlorination products are related to the E actor for the abstraction of different classes of hydrogen atoms and the formation of corresponding alkyl radicals. In generally, the rate of abstractions of hydrogen atoms and the formation of corresponding free radicals is found to follow the order tertiary, secondary, and primary. First tertiary, then secondary, third primary. In fact, during chlorination at room temperature, the relative values of rates of abstractions for tertiary, secondary, and primary hydrogens has been found to be 5 ratio 3.8 ratio 1 per hydrogen. It is interesting to note that relative values of rates of abstractions of hydrogens also depends upon the nature of halogen used, as explained in next session. Thus, the relative values of rate of abstractions of tertiary, secondary, and primary hydrogens in brominations at 400 Kelvin has been found to be 1600 ratio 82 ratio 1. These are clearly quite different from the values in case of chlorination. Knowing the probability factor and relative values of rate of abstractions of different hydrogens, or in other words, their relative reactivities, it is possible to predict the ratio of isomeric halogenation products obtained from a given alkenes. For example, in the chlorination of N-butane, the reactive amounts of monochloro products found may be calculated as follows: CH3, CH2, CH2, CH3, and butane. Cl2 room temperature light gives CH3, CH2, 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 Cl plus HCl, and butyl chloride abstract of 1 degree. Hydrogen CH3, CH2, CHCl, CH3 plus HCl. The sec butyl chloride abstract of 2 degree H. N-butyl chloride divided by sec-butyl chloride equal to number of 1 degree hydrogens divided by number of 2 degree hydrogens multiply reactivity of 1 degree hydrogens divided by reactivity of 2 degree hydrogens. 6 by 4 into 1 by 3.8 equal to 6 divided by 15.2. The accepted ratio of two products calculated above is equivalent to 28% of N-butyl chloride and 52% of sec-butyl chloride. The actual percentage is found to be same. Problem 4.3. Compute the ratio in which N-propyl chloride and isopropyl chloride are likely to be formed by the chlorination of propane, given that the relative reactivities of 1 degree and 2 degree hydrogens in chlorinations are 1 ratio 3.8. Answer: N-propyl chloride divided by isopropyl chloride equal to number of 1 degree hydrogens divided by number of 2 degree hydrogens equal to multiply reactivity of 1 degree hydrogens divided by reactivity of 2 degree hydrogens is equal to 6 by 2 into 1 divided by 3.8 is equal to 6 by 7.6. Problem 4.4. What is the accepted percentage of N-butyl bromide and sec-butyl bromide formed by the bromination of N-butyl if the relative reactivities of 1 degree and 2 degree hydrogens in brominations are 1 ratio 82? N-butyl bromide divided by sec-butyl bromide is equal to number of 1 degree hydrogens divided by number of 2 degree hydrogens multiplied reactivity of 1 degree hydrogens divided by reactivity of 2 degree hydrogens is equal to 6 by 4 into 1 by 82 is equal to 3 by 162. Percentage of N-butyl bromide is equal to 98.18%. Percentage of sec-butyl bromide is equal to 1.82%. 4.11.5 Reactivity and selectivity, chlorination versus bromination. So it has been studied earlier that in the hallucination reactions of alkenes, chlorine is more reactive than bromine. It has also been discussed that in case of alkenes containing different types of hydrogen atoms, the ease of abstraction on reactivity of different types of hydrogen follows the order 3 degree, 2 degree, 1 degree, irrespective of the nature of halogen taking part in the reaction. But now we considered a very interesting observations with the help of a simple example. When propane is subjected to chlorination, N-propyl chloride and isopropyl chloride are formed in the ratio 45:55. But when propane undergoes bromination, N-propyl bromide and isopropyl bromide are found in the ratio 4:96. Keeping in view the number of primary and secondary hydrogens 6 and 2 respectively, it is clear that secondary hydrogens of propane are more reactive than primary hydrogens in both the cases. But there is much more selective abstractions of secondary hydrogens in bromination than in chlorination. In general, the reactive rates of abstractions of tertiary, secondary, and primary hydrogens of alkenes and chlorination at room temperature are 5.0 ratio 3.8 ratio 1. While the bromination at 400 Kelvin, the relative rates are 1600 ratio 82 ratio 1. This means that bromine is less reactive but more selective in its reaction with the different types of hydrogens. On the other hand, chlorine is more reactive but less selective. This is in accordance with reactivity selectivity principle, according to which if the attacking species is more reactive, it will be less selective, while a less reactive species is more selective. To understand the above principle, let us consider the transition state involved in the rate controlling step, that is the attack of halogen free radicals on alkenes, of chlorination and brominations of alkenes. The reaction of highly reactive chlorine atoms with alkene has very low E act, and therefore the transition state is reached quite early when the alkyl radical character has just started developing. Therefore, the stability of alkyl radical ultimately formed does not have much effect on the ease of occurrence of the reaction. RH plus Cl highly reactive gives RHCl reached quite early. Alkyl radical character just beginning to develop gives R radical plus HCl. In case of much less reactive bromine atom, the above step involves a high EACT, as such a transition state is reached very late when sufficient alkyl radical character has already developed. Therefore, the transition state resembles the ultimately formed free radical in its stability and ease of formation, that is 3 degree, 2 degree and 1 degree. RH plus Br low reactivity gives RHBr reach quite late. Alkyl radical character sufficiently developed gives R radical plus HBr. In other words, bromine atoms will attack the tertiary hydrogen relatively much more easy than a secondary, which in turn would attack more easily than primary hydrogens. Hence, as compared with more reactive chlorine, there will be much more selectivity in the reaction with less reactive bromine. 4.11a Interconversions of alkanes. During the study of organic chemistry, we have often required to prepare one organic compound from another. Sometimes this may involve preparation of higher members of a class of compounds from a lower member, stepping up a series, or vice versa, stepping down the series. We now illustrate the procedure followed by considering the interconversions of alkenes. For 11a, first preparing our higher alkanes for our lower members. So this involves the following steps. First, chlorination or bromination of given alkane into monochloro derivatives. Second, Wurtz reaction or Corey-House reactions of the monochloro derivatives obtained with a suitable alkyl halide or lithium diallyl copper as required. For example, methane may be converted into ethane as follows: CH4Cl2, presence of light gives CH3Cl, then gives Na in presence of Na, dry ether Wurtz reactions gives CH3CH3. Ethane may be converted into propane as follows: CH3CH3 in presence of Cl2 gives CH3CH2Cl in presence of CH3 twice Cu. Li Corey-House reactions give CH3CH2CH3. 4.11.8.2 Preparing a lower alkanes from a higher one. This involves the following steps. First, conversion of given alkanes into alkyl halides. Second, hydrolysis of alkyl halides obtained to get an alcohol. Third, oxidation of alcohol formed into a carboxylic acid. For decarboxylations of the acid, its sodium salts to form the alkane. For example, ethane may be converted into methane as follows: CH3CH3 in presence of Cl2 gives CH3CH2Cl. In presence of NaOH, aqueous NaOH gives CH3CH2OH. In presence of OK2Cr2O7 as H2SO4 gives CH3COH. In presence of NaOH gives CH3CONa. In presence of NaOH plus CaO heat gives CH4. Thank you.